Hello everyone. In today's project video, I will show you how to build an AI-powered video Q&A application that you can run locally and that lets you chat with videos in a new and interesting way. I know that many AI tools like Google's Notebook LM, ChatTube or Screen App, and many others allow you to chat with videos. However, they all focus solely on audio transcripts, leaving the visual elements completely ignored. So what if we need to extract information from those visuals? Because in many cases they hold most of the information. Well, then we need a different approach that can take us one step further. So here in this video, I will guide you through building a simple yet powerful video Q&A solution based purely on the visuals of the video. And to do that, we will be using vision language models combined with computer vision techniques. And before we start discussing this approach, let me show you a great use case for it. So as you may know, CCTV footage often records silently through the night, making it an ideal use case for our application. So for example, we have here a CCTV footage. We start first by extracting the main keyframes along with their timestamps. Then we use a vision language model to generate captions and descriptions for these keyframes. Then finally, using an LLM, we summarize the video into chronologically ordered chapters. So this way, we don't need to watch the whole video to know if something interesting had happened, and you can simply read the summary and jump straight to the timestamp we pick. Okay, so this is one of many use cases for this approach, and I will show you some of them in this video. Okay, so now I will briefly discuss this approach, and then I'll show you how to implement it using Python. So basically, to give a chatbot the ability to watch a video or ingest its visuals, we need to convert those visuals into textual information. And to do that, we will use a vision language model. But doing that is quite challenging because usually videos contains a huge number of frames, depending obviously on their duration and the FPS. So obviously we need to reduce the number of frames, and for that we will be using optical flow estimation. Now I know that there are models that can perform video captioning, meaning that they can take as input short video clips. But for this project, I wanted to run the solution locally, so I chose to use an image captioning model instead. Alright, so one last thing I need to note. This approach isn't suited for all types or kinds of videos. So for example, sports videos or science experimentation videos aren't well suited for this approach. However, we can get really good results for other types of videos like lecture slideshows videos, CCTV or trail cam videos, and also some cooking videos. Okay, so now that you have a general idea about this application, let's start coding right away. So here we have our notebook, and as always, you can find these project files on my GitHub. So first we need to import few libraries. We need to import time. Also, we will import datetime and NumPy. We need video from IPython display to display or play the video in our notebook. And Mellow to read images. We also need the QDM for our for loops. Next, we need to import OpenCV. We need also to import Torch. And now we need to import the libraries required by the VLM we're going to use, which is MonoInternVL. So we need the transforms module from Torch Vision, also the interpolation mode from Torch Vision as well. And then we import the usual modules from transformers. So here we have auto model, auto tokenizer, bits and bytes config, and we're gonna use blip2, so we need the blip2 processor and blip2 for conditional generation. And finally we need the Grok library for the Grok LLM APIs. And we're done with the imports. So next, I usually check for CUDA availability to make sure that we're running Torch on our GPU. And currently I'm using Codium as my copilot. So actually it's a good practice to express what you need to code in a comment first. That way the copilot will be able to help you much better. Then we need to set our video path. So this is the path for the video that we're gonna process. And here I have 4 demo videos. We'll choose, for example, the cooking video. And we can play it using the video module from IPython display. So here we have it. So this is a fast-paced cooking video, and we will be trying to extract the information such as the ingredients and the cooking procedure using our approach. Alright. So now we will start with the video preprocessing. So let's first define some constants. We will need the display width, display height, output width, and output height, and output FPS. So we will need the output width, height, and FPS in case we will save the processed video. Then we need to define the motion threshold and the pixel count threshold. And we will use these thresholds for the motion detection using the optical flow. Alright, so now let's calculate the far and back optical flow. So it's better first that we start with a demo where we visualize the output so we can better tune the parameters. So we set first the save output variable to false because we don't need to save the output for now. Then we start first by reading or loading the video. After that we need to read the first frame because the optical flow is calculated based on 2 frames or 2 consecutive frames. So we need to get the first frame ready. And let's resize the frame using the display width and height. And then we need to convert it to grayscale mode because that's a requirement for the far and back optical flow algorithm from OpenCV. Then let's set our video writer in case we need to save the output. And here we're using the codec for the MP4 files. And you can use, for example, xvid for the .avi video files. And now we can start the while loop. So we will loop over the frames and we calculate the optical flow for each 2 consecutive frames and display it, of course. So we start by reading the next frame. Then we resize it and convert it to grayscale. And after that, calculate the optical flow. So here we have the code ready from our copilot. And these are the default values for the optical flow function. Then we need to calculate the magnitude of the optical flow. So to do that, we convert the coordinate from Cartesian to polar using OpenCV. And then we create a binary mask where the magnitude exceeded our predefined threshold. And after that, we calculate the number of pixels where we detected motion. So based on the number of pixels where we detected motion, we can say whether we detected motion for this frame or not. And for that, we have the pixel count threshold that we defined earlier. And in such case, we can print a statement saying motion detected, along with the average magnitude of the optical flow. So now we want to display the optical field as a vector field, and for that we need a copy of the current frame. So first we set parameters for the vector field. So we will display a vector field using a grid with step size of 16. And then we need to loop over the x and y coordinates. We get the flow vector at that point. Then we draw the arrowed line representing the flow vector. So here we want the arrowed line to be green. Then we set its thickness to 1 and its tip length to 0.5. Next we need to convert the binary mask to BGR mode so that we can stack the motion mask with the vector field image and the current frame image together to be able to display them all at once. So now we can stack the images horizontally into one single frame. And then we can add the text for the average magnitude of the optical flow. And finally, we can display it with OpenCV. Alright, so that's it for this iteration. We need to update the previous frame for the next iteration, of course. And then we need to treat the case where we save the output and the exit key. In this case, I usually want to use the escape key instead of the usual Q key. And finally, we release the resources and destroy all windows when we exit our while loop. Okay, so let's run it and see the outcome. we have an error here, too many values to unpack. So here we used frame2.shape, but we only need the height and width. So maybe we should use the grayscale mode of the frame2 so that we don't have that extra dimension. Let's run it again. Alright, we have another error. Can't parse pt2 sequence item index 0 has wrong type in arrowed line. So let's check that line. Alright, so here I forgot to cast these coordinates to integers. So hopefully it ran correctly this time. And there we have it. So here we have on the left the actual frame of the video, and then in the middle we have the optical flow, and on the right the binary mask, where actually the motion exceeded the threshold we set. We should maybe elongate that rectangle under average motion magnitude for a better display. We simply need to use here the display width and height. So let's say we use display height divided by 5. It's still very large, so let's try divide by 10. And it's perfect. Alright, so as you can see, using those thresholds, we detected less motion. We can, for example, lower the motion threshold to make the motion detection more sensitive. But since we have too many movement and very drastic motion in this video, let's keep it at 15. Alright, so now we've seen how we detect motion for each frame, and we're gonna use that to reduce the number of frames. So we will repeat the same process, but this time we need to create a frame list where we will save the frames that we need to keep. Then we load the video as we did earlier. We read the first frame. And now, since we're going to extract frames, we need to keep track of their timestamp. So we will start first by appending the first frame with the first timestamp, which is 0 minutes and 0 seconds. Then we convert the frame to grayscale. So we need to get the frame count of our video to instantiate our TQDM progress bar. And then we can start our while loop. So as we did, we read the next frame. Then we get the current frame timestamp. So to do that, we get the current position in milliseconds using OpenCV. Then we divide it by 1000 to convert it to seconds. And then we round the number and convert it to integers to get the frame time in seconds. After that, we can easily convert it to the format we need in minutes and seconds using div mod. It's actually the same as using frame time divided by 60 and then frame time mod 60. And then finally we format the timestamp into the minute and seconds format that we need. Next, we resize the frame as we did earlier and convert it to grayscale to be able to calculate the optical flow. And now we can calculate the optical flow, calculate the magnitude and the motion mask, and then the number of motion pixels. And once we detect motion in the current frame, we don't need to print any messages. We just need to convert the current frame into RGB mode and then append it to our frame list. So basically now we're done with this while loop. We just need to update our previous frame for the next iteration. And then release the resources once we exit our loop. And let's run it. So as you can see, this video contains about 4,600 frames. So I will fast forward to the end. Alright, so now we have the list of frames where we have detected motion. So let's visualize our reduced video. To do that, we need to load our video to get the frame count. And then we can print the original video frame count and the reduced video frame count. And as you can see, we went down from 4,600 to 2,500. It's quite a huge reduction of about 1/2. We can also visualize the frame list as a video. So to do that, we need to create this play video function to play the video in 30 FPS. So we set a delay between frames of about 1000 over 30. And then we loop over the frames and display them. Of course, we set the exit key and we destroy all windows when we're done. So let's play the reduced video. Okay, so we stored the images in RGB, and you know that OpenCV treats images in BGR mode, so that's why we see the images in blue. We need to convert the frames to BGR before displaying them. So let's run it again. Alright, now it works perfectly. Now the video is, I feel like it's still very long, so maybe we can reduce it even further without losing much information. So we will reduce the video to 1 FPS, meaning that we will only keep 1 frame per second. So we have a list of frames with their timestamp. We will loop over those frames and compare the timestamp progressively, and each time we find that the difference of the timestamps we have is less than 1 second, we will delete or omit that frame, and we will only keep the frames where we have a difference between each 2 consecutive frames more or bigger than 1 second. So to do that, we need to create a function that calculates the timestamp difference. So it takes 2 timestamps as input. It calculates the difference in seconds and it returns it. Alright, so now to reduce the video to 1 FPS, we will initialize a new frame list with the first frame. And then we need to loop over the remaining frames. We calculate the timestamp difference between the last frame on our new list and the current frame from the frame list. And if that timestamp difference is bigger or equal to 1 second, we append the current frame to our new list. Alright, so now let's print the newly reduced video frame count. So we have the previous reduced video frame count and the new reduced video frame count. So we went down from 2500 frames to about 170 frames, and that's actually really good. So now let's play the new frame list. And as you can see, it's actually like we've created a time lapse of the video, but we've kept the most important frames where we detected motion. So these are the frames that count and that hold more information that we can use. So now we're moving to the second part of this project. Actually, let's name the first part Part 1, where we pre-processed the video. And then we have Part 2, Video Captioning. So here we will use two models. We'll start by using Blip2. So this is actually a very well-known model for image captioning. So we can import it easily from transformers using its path from Salesforce. So we start by importing the Blip model with quantization. So we will be using the Blip2 2.7 billion model. And we set the quantization configuration to 8-bit. So the first time you run the cell, it will take much longer because it will need to download the model from Hugging Face. But I already have it on my machine. So it's imported correctly, and you can check the task manager to see if it's imported on your GPU or not. Next, we will loop over our frames and generate captions for each frame. And to do that, we will create a Blip2 caption list. And then we will loop over the frames. We will pre-process or process each frame using the Blip2 processor. Then we generate a caption for it using max length of 100. Next, we need to decode the caption to be able to get it in a text format. And then we append it to the Blip2 caption list. Okay, so let's run it. So we have a runtime error, shape mismatched, value tensor of shape cannot be broadcasted to indexing results of shape 0. So this is the first time I've seen this error. It's related to the .generate method. Let's check it real quick on the internet. So let's first make sure that we're using the correct code to run the model. So here in 8-bit precision, we're using the Blip2 processor, Blip2 for conditional generation. Let's check the community. Alright, what do we have here? So we have a runtime error, shape mismatch. It's actually the same error we got. I'm now seeing this error being returned when captioning, and I have no idea how to resolve it. The model had been working previously a couple of weeks ago. Now return to it when using for captioning. I see this. Has anything changed? Okay, so it seems like it's a problem with the current version of the model or the current version of the transformers library. In any case, we don't need to waste time on this. Let's use the other model. We can use instead monointernVL, and in case you're not familiar with monointernVL, I've just made a video about it. You can check my previous video to see its capabilities and how to run it locally. And it needs a certain version of transformers to be able to run it. The transformers 4.37.2, so we need to install that. So now we need to restart our kernel and rerun the whole notebook. And let me delete the blip2 modules that we imported earlier. So let's run the main cells we need. So in the meantime, while the preprocessing step is running, let's get the monointernVL preprocessing code ready. So as I said, you can find the code on my GitHub. So here we need to import these constants and few helper functions. So we need the build transform function, define closest aspect ratio function as well, then the dynamic preprocess function, and finally the load image function. Then we need the code to import the quantized version of the model from Hugging Face. And as a final step, we get the generation config dictionary. So now we're ready to use the monointernVL model to generate captions for our frames. And we will repeat the same loop that we used earlier for blip2. Unfortunately, blip2 had some issues and we couldn't run it. So we create a captions list. And then we loop over the frames. We load and preprocess the images or frames using the helper functions we just copied. Then we simply create our prompt. So we use the image tag to indicate that we have an image. And then we ask, for example, describe the image and what it contains concisely. And start with, for example, this frame depicts. Then using torch nograd, we run the model.generate. And we pass it the prompt and generation config. Finally, we add the generated caption to our captions list. Alright, so apparently here there is a new version of monointernVL on Hugging Face and it's trying to download it. Alright, so now the model is ready and we can run this for loop. we have an issue here. Attribute error, numpy and the array object has no attribute read. So actually here we copied the load image function from GitHub, and it takes as input the path to an image file. But in our case, we have already the images in a list, so we need to change this image reading line. And instead of using image.open, we will use image from array to convert the image from a numpy array to a pillow object. And let's correct the argument description here. So now let's rerun this cell. Alright, so as you can see, it's running and it's estimated to take very long to finish. So what I will do here is that I will skip to the end and I will run the cell for only the first 30 frames. So it won't take that long. And actually it's taken too much because it's running locally. That's the first thing. And the second thing, because I'm recording, so that takes a toll on the computing power. But if we have this model hosted on a cloud service, we would be able to run it in only a few seconds. Alright, so here we have the loop completed for the first 30 frames. And let's see the caption list. Alright, as you can see, we have each caption with the timestamp. And for example, we have the first frame depicts a close-up view of several blue-colored crystalline structures, intricately arranged and spread over what seems to be a purple fabric or surface. So basically this is a description of the frame, and that's what we have for the remaining of the captions. And as you can see here, the captions varies in length, and they try always to capture the essence of what's happening in the image. And that's really a strong point for this model. I tried first to run the blip2 model to show you the difference between both caption generators, and to show you that this actually performed better, because when I tried it with the blip2 model, it usually generated very short captions where it describes the frame in a more generic way and a more general overview without capturing most of the details and without, for example, reading the text that's written on the image. So for example, if you see here, it says this frame depicts an olive oil container with text indicating the quantity 1 tablespoon. And in the next caption as well, it mentioned 1 tablespoon, which is a written text on the frame. So this model performs better in this aspect. Alright, so let's move on to the next step. So now we will perform video Q&A and summarization. So to do that, we will be using a large language model from the Grok API, which is a free API, or an API that has a free tier. And to do that, we will create a .env file where we need to store the Grok API key. And that's a good practice. You shouldn't store or write the API key on your notebooks. Always try to use a .env file for more securely usage of API keys. And then if you're pushing your code to GitHub, don't forget to add the .env files to your gitignore file so that you don't accidentally push your API keys to a public repository. And to be able to access the .env file, we need to install the python.env library. So from .env we import the load.env function, and we use it to import the variables from the .env file as environment variables. So then we can easily access those variables using os.getenv. And you can, for example, print it to check if it's imported correctly. Alright, so then we need to create a function to respond to a query based on the generated captions. So this function would take as input the list of captions, the query, and the Grok client. So we need first to define our Grok client using our API key. And we have an issue here with the grok class, so let me check the imports. So here we actually need to import the grok class from the grok library. And let's now finish our generate response function. So first we will convert the list of captions that we generated using MonoInternVL into single text that the LLM will use as context to respond to our query or question. Then we define our chat completion from the grok client. And we set the list of messages within it. So for example, here we can set up a simple prompt stating based on the following chronologically ordered or sorted frame captions. Where each line has a timestamp and the frame caption. Then we pass the query, and then we pass the text that we created from the captions list. Finally, we need to select a model, so we'll be using a llama model. Let me first check its name on their website. So this is it, we'll be using the llama 3.1 70 billion versatile. And then we return the message content of the response. So let's start with a simple query. Let's say summarize this cooking video into chapters with timestamps. And then we generate an answer. So let's print the answer. So based on the given frame captions, the cooking video can be summarized into the following chapters with timestamps. Chapter 1, Introduction, from 00 to 004. And the first few frames introduce various food items such as pizza, tortilla chips, and creamy potato, etc. Then the Chapter 2, Pasta Preparation. Chapter 3, Mixing Ingredients. Chapter 4, Cooking and Mashing. Chapter 5, Working with Dough. Chapter 6, Baking and Preparing Sauce. Alright, that's good. Let's try another query. So here we can ask, for example, what is the recipe with ingredients used to prepare the pizza? And describe the method of preparation. Alright, so based on the provided captions, it is possible to reconstruct the recipe and preparation of pizza, focusing on the frames related to pizza preparation. Ingredients: 2/3 cup of light and powdery flour, garlic salt, marinara sauce, mozzarella cheese, etc. And then the preparation method. And it also cites the timestamp for each step. That's really impressive. Alright, so this is for the cooking video. Now let's try another video. And to do that, I need to restart the kernel, because as you can see, the GPU memory is almost at max. So for our next video, we will try this simple course slideshow from MIT OpenCourseware. And this is a course about simple properties of probabilities. So it discusses some axioms of probability and the rules used for calculating the probability of disjoint events. Alright, so let's run the pre-processing and the captioning, and I'll skip to the end of this so that you don't need to wait. Okay, so for the first query, let's ask similar things. Let's say summarize this educational video into chapters and maintain the chronological order. Alright, so now let's ask it to generate a question or a test question. So the question, suppose that you have three disjoint events, A, B, and C. The probability of A, PA is 0.4, the probability of B is 0.3, and the probability of C is 0.5. What is the probability of the union A, B, and C? Alright, so that's a great question. Let's try to ask it now to generate three test questions with answers. Alright, so the first question, what is the interpretation of the equation PA bigger than 0 in the context of atomic axioms? Then the second question, what is the interpretation of the equation P of omega minus 1 in the context of atomic axioms? Question 3, what is the formula for probability of disjoint events in the context of atomic axioms? That's really amazing and quite impressive. So as you can see, we have many use cases for this approach, and I hope that I made it clear for you and simple to follow. Alright, so that's it for this application. As you can see, we have many use cases for this approach, and I hope that I made it clear and simple to follow. And that's it for this video. I'll see you in the next one.